Charles' law. Charles' law relates temperature and volume. It is the ratio of the volume to the temperature, named after Jacques Charles. Now, what it says is that if we have a gas contained inside of a container like this piston here or syringe, if we heat it from say 25 degrees to 65 degrees, the gas inside of there will expand. The air molecules will move faster, they'll hit the piston or the plunger and expand, making the volume get bigger. Now, that's assuming that the pressure, in this case maybe atmospheric pressure, stays the same. That's pushing down on the top of the piston, and that pressure remains the same throughout. Also, the number of gas molecules in there would have to remain the same too as well. Charles' law: increase the temperature, increase the volume, and vice versa. This would be a direct relationship. One goes up, the other one goes up. Here's a quick demonstration in Charles' law. We have a bottle with a balloon, a certain volume of air, and some boiling water. If we put the bottle into the boiling water, the air expands as it gets warmer. All right, here's one of my favorite Charles' law experiments. Start with a garbage bag, very thin plastic garbage bag. Works great for making hot air balloons. I'm going to tie one side off with a knot. Go to the other side, tie it off with a knot. Still have an opening right there. Piece of string, that's for ballast, to kind of weight it down. Tying a loop on one end, I'm going to put that over the one knot. Tie a loop on the other end. Put that over on the other knot. And we have a hot air balloon. To blow it up, we'll use a hair dryer. Now, as the air heats up, it expands, gets larger in volume. Some of it comes right out of the bottom. So the air that's left inside has less density, and it floats. We have a hot air balloon. Exactly how hot air balloons work that people ride in, except it's flame that makes the air get hot on the inside. Right? Right? As opposed to Boyle's law, remember that Boyle's law is an inverse relationship, whereas Charles' law is a direct relationship. Now, this ratio of volume to temperature is always the same. If we increase the temperature, then we increase the volume, but the ratio, the quotient of volume to temperature always remains the same. Some value, a constant called Charles' law constant, which depends on how much gas there is and the pressure of the gas. Now, assuming that that stays constant, this would be true. If we made a graph of Charles' law, we would take the equation V over T is K and solve it for V, and it follows the form of Y equals mx plus B, the equation for a straight line. If we put it on the graph, then we would have a straight line, and B is the intercept. That is when the temperature is 0 degrees, in this case degrees Celsius, the volume would be a certain value. Now, remember that you can go below 0 in Celsius. So if we extrapolated, that is, stretch this line down to when it hits the axis, we are going to at some point have 0 volume, and the corresponding temperature then would be what we call absolute 0. All right, so that's how we arrive at absolute zero, the coldest anything can get. So if we shrink a gas by cooling it down, when its volume reaches zero volume, you couldn't get any smaller. And the temperature then would be what we call absolute zero in Kelvin, or negative 273 in Celsius, or a negative 460 degrees in Fahrenheit. Absolute zero. Let's do some sample problems. Now, when doing calculations using Charles' law, a couple of rules we have to follow. One is that we must have our temperature in Kelvin. It has to be on an absolute scale. As far as volume is concerned, we can measure that in any volume unit we want. Centimeters cubed, liters, decimeters cubed, which is the same thing as a liter. It could be in any units. But temperature must be in Kelvin. We have to use absolute scales when doing calculations so that we don't divide by zero. As far as volume is concerned, any zero volume, whatever the unit is an absolute measurement. You can't get any smaller than zero volume, no matter what unit you use. In the case of temperature, you could go negative if you're in Celsius or negative if you're in Fahrenheit, but on the Kelvin scale, we cannot go below zero. That's our absolute scale. So when doing temperatures, we have to convert the temperatures from Celsius into Kelvin. Remember how to do that? We just add 273. So 61 degrees Celsius plus 273 gives us 334 Kelvin. 35 plus 273 gives us 308 Kelvin. Now we are set. To solve Charles' law for V2, we would write V2 equals V1 divided by T1 times T2 on the top. All right, V1 is 85 centimeters cubed. T2 is 308. T1 is 334. Calculator says 85 times 308 divided by 334, 78.4. 78.4. Now that would be in centimeters cubed. Centimeters cubed. All right, let's try the last row here. V1 is 2.0 decimeters cubed. V2 is 4.99 decimeters cubed, and they match, so we're good to go. T1 is in Kelvin already, 263, and T2 then is what we're looking for. Now, if I solve Charles' law for T2, this one can be a little bit tricky because T2 is in the denominator, and we have to get it out of the denominator. So if I move it to the numerator on the left side and then move V1 to the denominator on the right side, I end up with V2 divided by V1, and then T1 moves to the right side on the top, T1. So solving for T2, get it out of the denominator. And then we have V2, 4.99 times T1, 263, divided by V1, 2.0,